Hello everyone, my name is Yishu Du. I'm a first-year PhD student from ENS Lyon, France. I'm very honored to give this speech here. Today, I want to present our work, which name is Robustness of the Daly formula for stochastic iterative applications. The Daly formula for periodic checkpointing is known to hold for a divisible mode application, where one can checkpoint at any time step. This paper assesses the accuracy of the formula for applications decomposed into computational iterations. Hence, we established that the relevance of the formula goes well beyond its original framework. I would like to give my talk as following. At first, I will introduce the background and the previous work of our study. Then, I will present the model and the organism we proposed. After that, I will present the simulation result, which shows the performance of our organism. Finally, I will conclude our work and discuss what we can do in the future. So first of all, please let me introduce the introduction. For the moment, we are on the road to exascale. From the figure here, we can see the high performance development since 1994. Using the blue curve as an example, we see the total power of the top 500 supercomputers slows down since 2013. So what are the barriers on the road to achieving exascale? In February 2014, the Advanced Scientific Computing Advisory Committee published the top 10 challenges to achieve the development of an exascale system. In this paper, we focus on one of those named resilience. So what are the causes and what are the solutions? Supercomputers enroll huge numbers of processors. We assume that the mean time between failures of each individual component is μ_n. Then the MTBF of the whole system decreases linearly with the number of processors p. Most powerful computers in the top 500 list are victims of at least one failure a day. At exascale, MTBF is around 5 minutes. So fault tolerance techniques to mitigate the impact of errors are required to ensure a correct and uninterrupted execution of the application. Actually, there are two types of faults, permanent faults and transient faults. This paper focuses on permanent faults, which also known as field stop errors. They usually due to hardware failures or crashes. When field stop errors occur, the effects include the following. They can be quickly detected. The execution stops. The entire content of local memory is lost. Computation has to be restarted from the last checkpoint. Checkpoint restart algorithms are widely used to handle field stop errors. We save the intermediate data onto stable storage and re-execute from the last checkpoint in case of a failure. Next, let me introduce our model. The expected execution time to perform a work of size W followed by a checkpoint of size C in the presence of failures with a restart cost R and a downtime D is as follows. We assume that failures can strike during checkpoint and recovery, but not during downtime. For more details, we recommend the Springer monograph on resilience in 2015. The objective is minimizing the expectation of the execution time or makespan. The state of the application is periodically checkpointed, and when failure occurs, one recovers from the last valid checkpoint and resumes the execution from that point on, rather than starting the execution from scratch. The key for an efficient checkpointing policy is to decide how often to checkpoint. Indeed, checkpointing too often leads to spending too much time in checkpoints, as opposed as to executing useful work. On the contrary, checkpointing too infrequently leads to wasting too much time to re-execute work that has been lost after a failure. Yang and Daly derived the well-known Yang-Daly formula for the optimal checkpointing period. PYD is equal to the square of 2 mu fc, where mu f is the platform MTBF and c is the checkpoint time. However, many scientific applications exhibit a more complicated behavior. In this work, we focus on iterative applications, which we define as applications that are decomposed into computational iterations. There are two assumptions. First, because each iteration is state-dependent. When considering an iterative application, we assume that the length of each iteration is not known in advance. The duration of an iteration is stochastic, that is to say, it obeys a probability distribution law D of min mu D. Second, one can checkpoint only at the end of an iteration because the volume of data to checkpoint is dramatically reduced at that point. We consider an iterative application composed of n consecutive iterations. The execution time of each iteration is not known before execution, but follows a probability distribution D. The execution times of the iterations are thus modeled with random variables x1, x2 until xn, where the xi are independent and identically distributed variables following probability distribution D. A solution with m checkpoints writes as s is equal to dirt1, dirt2 until dirt_n, where dirt_i is equal to 1 if and only if we perform a checkpoint after the s iteration of length xi. We let i1, i2 until im denotes the checkpoint indexes, and wj denotes the work between two consecutive checkpoints. Next, let me introduce our first algorithm, stochastic strategy. Considering an iterative application with n iterations of wi, we are interested in minimizing the total execution time of the application. This mixspan is given as follows. Static solution decide which iterations to checkpoint. One can choose a solution to be periodic with period k, that is to say, checkpoints are taken every k iterations, namely at the end of iterations number k to k until the last iteration. An optimal solution may not be periodic. However, we prove that the periodic solution with period k static given in the theorem is asymptotically optimal when n is large, and then we show in the proposition that the first order approximation of the period length corresponds to the Young-Daly formula. Next, let me introduce our second algorithm, dynamic strategy. In the static strategy, we have studied static solutions where checkpoint locations are decided before the execution. These static decisions are made based upon the distribution D and the fault rate, but do not depend on the actual length of the iterations in a specific instance of the problem. However, when executing the application, we know on the fly whether some iterations has been much shorter or much longer than the average iteration length, and we could take the information into account to decide whether to checkpoint or not. In other words, we take dynamic decisions at the end of each iteration, and these decisions are based upon the actual work executed since the last checkpoint. The dynamic strategy can be stated as follows. First, we fix a threshold WTH for the amount of work since the last checkpoint. Then, when iteration xi finishes, if the amount of work since the last checkpoint is greater than WTH, then sigma I is equal to 1, means we checkpoint. Otherwise, sigma I is equal to 0, means we do not checkpoint. We make dynamic decisions at the end of each iteration based upon the overhead of the decision. The slowdown h is defined as the ratio h is equal to actual execution time divided by useful execution time, so that the slowdown is equal to 1 if there is no cost for fault tolerance, no checkpoints, no re-execution after failures. We would like to minimize the slowdown at each step. When iteration is completed, we compute two values. First, the expected slowdown HCKPT means if a checkpoint is taken at the end of the iteration, we assume that we just finished an iteration and that the total amount of work since the last checkpoint is W by n. The expected time to compute W by n was T W by n 0 dr, and the expected time to checkpoint now is T 0 cdr plus W by n, and the useful execution time is W by n. Second, the expected slowdown h0 means if no checkpoint is taken at the end of this iteration, if we do not checkpoint now but only at the end of the next iteration of length x, which is drawn from distribution D, the actual execution time will be Tw by n 0 dr plus Tx cdr plus W by n, and the useful time is W by n plus x. If hckpt is smaller than h0, it is better to checkpoint now than waiting for the end of the next iteration, and by induction than waiting for the end of two or more following iterations. On the contrary, if h0 is smaller than hckpt, it is better not to checkpoint now, in which case we recompute the decision at the end of the next iteration. By definition, WTH is the threshold value where hckpt is equal to h0. Finally, we derive the threshold value WTH as follows. Then, in the proposition, we show that the first-order approximation of the threshold WTH corresponds to the Daly formula. Next, let me introduce the experiment results. First, let me detail the experimental methodology. For the application scenarios, we consider an iterative application composed of n is equal to 1000 consecutive iterations. The execution time of each iteration follows a probability distribution D with mu D is equal to 50 and the standard deviation sigma. There are three default instantiations for three distributions: uniform 2080, gamma 25 0.5, and normal 50 2.5 square. For the failure scenarios, each iteration fails with probability p-fail is equal to 10 to the power of minus 3, 10 to the power of minus 2.5, until 10 to the power of minus 0.1. For example, p-fail is equal to 10 to the power of minus 3 means one failure may occur every 1000 iterations. For the checkpointing codes, checkpoint times c is equal to eta times mu d, where eta is the proportion of checkpoint time to the expectation of iteration time. Recovery time r is equal to c, and fixed downtime as d is equal to 1. We evaluate the make span with 10,000 random simulations. Next, let me present the static strategy results. This figure is the performance of the static strategy that chooses the value of k. The black lines correspond to its mean. Brown-red diamonds plot theoretical make span. The horizontal axis is the value of k. The vertical axis is the make span normalized by that of the static Daly strategy. The first important result from the plot is the experimental validation of our model. Indeed, the black lines and the diamonds are almost identical for all k values. The closer we get to the optimal value k static, the closer the theoretical make span gets to the simulation make span. In particular, for k is equal to 5, the theoretical make span and the simulation make span are exactly equal, leading to a ratio of 1 in all cases, so the box plot contains a single value. In order to compare static strategies with dynamic strategies, we plot blue and red lines corresponding to the optimal dynamic strategy and the Daly dynamic strategy, respectively. Both lines are very close to 1, meaning that these two dynamic strategies have the same performance as the optimal static strategy. The conclusion in this table agrees with that in the last figure. We can see that the optimal simulation parameter K-sim, the optimal theoretical parameter K-static, and the first-order approximation of the Young-Daly formula KFO are always the same. Overall, the conclusion of the static results is that the simple strategy based on the Young-Daly setting remains a good and robust solution for stochastic applications and can safely be used in this context. Next, let me present the dynamic strategy results. The figure is the performance of the dynamic strategy that chooses a threshold of gamma times WTH, where gamma is from 0.1 to 2. The orange and the purple line represents the mixspan obtained by the optimal static strategy and the Young-Daly static strategy, respectively. As in the last figure, these ratios are very close to 1, meaning that static and the dynamic strategies given similar results both when using optimal parameters or the one approximate using the Young-Daly formulas. The conclusion in this table agrees with that in the last figure. We can see that the optimal simulation parameter WSIM and the optimal theoretical parameter WTH are always the same. Contrarily to the static case, WTH and WFO are slightly different. However, the performance obtained in the last figure are similar. And again, the Young-Daly formula seems a safe bet given its simplicity of use. In order to study the sensibility of our results to the failure probability, we compare the mixspan obtained by the static Young-Daly approximation with the mixspan obtained by the simulation when using the optimal static or dynamic strategy. We observe that the first two mixspans are always equal, because in all cases, KFO is equal to K-static. The optimal dynamic strategy is sometimes slightly better than the static ones, but with a very small gap for all failure probabilities. Next, we vary the standard deviation sigma of each distribution of execution times. Again, there is no difference between K-static and KFO in all tested cases, leading to a ratio constant and equal to 1. The optimal dynamic strategy is again very close, even for very large deviations. Finally, we vary the proportion eta of checkpoint time to expected iteration time. As expected, both the optimal K and W increases together with checkpoint time. The optimal static and dynamic strategies are still very close, even for very large checkpoint times. In conclusion, we have introduced and analyzed the checkpointing strategies for iterative applications. First, for static solutions, we derive a closed-form formula to compute the optimal checkpointing period, and we show that its first-order approximation corresponds to the Young-Daly formula. Second, for dynamic solutions, we derive a closed-form formula to compute the threshold at which one decides either to checkpoint or to execute more work. And we show that its first-order approximation also corresponds to the Young-Daly formula. Third, we conduct an extensive set of experiments with classic probability distributed, and we can conclude that the Young-Daly formula remains accurate and useful in a stochastic setting. Future work will be devoted to extending this study to iterative applications composed of several tasks. Non-constant checkpoint time is also a challenging problem. That's all for my talk. Thank you very much for your listening.